All right. Okay. Hello, everyone. Welcome back. I hope you all had a good weekend. Um, Today is the deadline for assignment 4 on static analysis, and I was looking on Marmoset, and most of the groups are done or almost done, or at least doing pretty well on assignment 4. So you have until the end of the day to finish that. And so we're in the home stretch, right? The course, there's only one more assignment left, assignment 5. I mean, it is a big one. But the thing I wanted to tell you is, in case your group doesn't get assignment 4 done, I think after today, you should shift to working on code generation, to working on assignment 5. Get your code generation working, and then maybe come back to assignment 4 later. The point is that code generation and assignment 5 doesn't depend on assignment 4. So if you don't get assignment 4 done, that doesn't stop you from working on code generation. You do need all of the earlier assignments, right? Assignment 1, assignment 2, assignment 3. You do need type checking, type information, name information in order to be able to generate code. But the static analyses, at least in Java and in Juice, are only there to detect bugs or potential bugs in programs. The results of those analyses are not used for code generation. The other thing is, just a reminder, assignment 4 is another one of the assignments that has a document where I want you to tell me how you did assignments 2, 3, and 4. So please do submit that document in time. And then finally, assignment 5 will also have a document like that for code generation. Okay, so we were doing code generation, and I have the board here from the last lecture, and I had the various kinds of data that we have to represent in Java or Juice, and the various places in memory, in the actual machine where we can put that data. And at the end of the last lecture, I kind of connected them up. How exactly you decide where to put all your data is partly up to you, up to the decision of your group. But I had some suggestions of sort of the easiest ways of doing this. So today I want to go into more detail on how to organize things in memory. And I'm going to look first. I need a pen here. All right. So I'm first going to look at the stack, and so specifically local variables, and how we might organize those on the stack. Okay. And so the idea is that we're going to put local variables at fixed offsets from the stack pointer. So if I call a method multiple times, maybe the method is recursive, each time I'm going to push more and more space on the stack. So the absolute addresses of those variables will be different, but for the currently executing method, the address of each variable will be at a fixed offset from the top of the stack, and it's this offset that the compiler needs to keep track of, right? So the compiler is going to assign each variable an offset from the top of the stack, and then every access to that variable that it sees in the Juice code, it will translate to a machine language access to that offset from the top of the stack. So just to do this by way of example, here's that for now, and wow. All right, so let's see. Okay, so all right. So let's say I have a method m, and in my method, let's say I have 3 variables. And in this case, they're all of type int, so they're all going to need 32 bits, so 4 bytes on the stack. But the part that I erased was the thing that we talked about last time about how different data types require different amounts of space. But for simplicity, you might want to use sort of the same size of data type for all the different Java data types, right? So that wastes some memory, but makes things more regular and a bit easier to manage. All right. So if I'm going to implement a method like this, if I kind of draw my memory here, and when I first get to the beginning of this method, let's say my stack pointer is pointing to some memory location, then the idea is that I'm going to push push 3 words onto the stack for the variables A, B, and C. Okay, so to allocate enough space on the stack to hold those variables, I need to move the stack pointer from pointing to the old top of the stack to pointing to the new top of the stack. Right, so here. So to set things up, to set up the space on the stack for these variables, I need to subtract 12 from the stack pointer. Right, so I'm going to have an instruction. So I can say subtract 12 from the stack pointer. And if you remember the way the instructions work, this is like saying ESP minus equals 12. So this takes the stack pointer minus 12 and puts the result back in the stack pointer. Okay. If I, alternatively, I could have written 3 push instructions. Right. I could have said, push 0. So push some constant value to be the value of each variable, and I need to do that 3 times. And now, with this setup, whenever my juice code accesses, say, variable A, well, if in the assembly language, I can just say ESP plus 8. So if I take the stack pointer, that's the address of the top of the stack. If I add 8, I'm going to go 4 bytes and 4 more bytes to get to the address of the variable A. And then when I put an address in square brackets in assembly language, that means dereference that address. So if I need to read variable A, I can just put this square bracket thing in my assembly language instruction, and that will give me the value of variable A. So I can use that in a move instruction, say, to load the value of A into a register. And I can store to A, again, by using this expression, right, this address in square brackets. Okay, and then similarly for B, that would be the stack pointer plus 4, right? So it's 1 word down, or in x86, it's 1 double word down, but anyway, 4 bytes down from the top of the stack. And for C, it would be ESP plus 0, or you could just say ESP, right? Plus 0 doesn't add anything. So the point is, in your compiler, you just keep a mapping from variables to stack offsets. So for A, it would be 8, B, it would be 4, C, it would be 0. And then you use that table to generate code to access these things. Okay, I'm kind of assuming that you saw something like this in CS241. Maybe that was a long time ago. If I'm missing some important things, do ask questions. So if you have questions or comments or whatever, do ask them in the chat. Okay. All right. So we're going to access variables like this. Now, this representation has a few problems. So sort of the biggest problem is that if I want my variables to always be at constant offsets from the top of the stack, then I can't move my stack pointer around, right? So for example, if I'm, now if inside my method, I do some actual computation, I might want to use the stack to implement that computation, right? If I have a complicated expression, I might want to put some of the sub-expressions, the values of the sub-expressions on the stack, which means changing the stack pointer. And as soon as you change the stack pointer, the sort of the difference between the address in the stack pointer and the address of each variable changes. So sort of problems with this approach are that the offsets change when using the stack. And so that's one problem. And another problem is, if I want the offsets to be fixed at compile time, I need the stack frame. So the frame must be a fixed size. And sort of what I mean by that is, and so in some programming languages like C, there are language features that allow you to allocate extra things on the stack, right? There's like the alloc A function in C that says, allocate some number of bytes of memory, but allocate them on the stack so that when this procedure returns, they will be popped off automatically. So it's like malloc that allocates on the heap, except it gets freed automatically for you. And but you can allocate any time within that procedure. So if I need to implement a feature like that, then I need to be able to move my stack pointer up, which again would mess up all of my offsets. Okay, so you don't need that feature for Java and for Juice, because there ahead of time exactly how many local variables you need on the stack. The compiler knows that. But for some languages, this doesn't give you enough flexibility. And just the idea of a stack frame. So this is the section of the stack for storing the variables of a method invocation. Okay, so every time you call a method, we allocate some space on the stack. In this case, we allocated 12 bytes. And so that's the frame for that particular invocation of the method. And of course, so the idea is that after the method finishes executing, you want to pop that space off the stack again. All right, and so that's called the stack frame. Okay, so I have these sort of problems with locating variables as offsets from the stack pointer. So the sort of the easy fix to these problems is to allocate to use a separate register, right? And this register is usually called a frame pointer, so the idea is that the frame pointer is going to stay constant within the method, so that the offsets will stay constant, and that way the stack pointer can change. Right. So use another register, and we usually call it the frame pointer. And in x86, the convention is to use the EBP register. All right, so what we're going to do is, I'll do this part in blue here, is that before we change the stack pointer here, we're going to save it. So I'm going to copy the stack pointer into the frame pointer. So, in my picture here, the frame pointer is going to point to where the stack pointer used to point. Okay, and the idea is that the frame pointer is going to stay constant throughout the procedure, and that way the stack pointer can move around all the time. And yet I can refer to the locations of the variables using the frame pointer. So for variable A, instead of being 8 bytes down from the stack pointer, it's going to be 4 bytes up from the frame pointer. So I'll have EBP minus 4, and for B, it'll be EBP minus 8. And for C, it'll be the frame pointer minus 12. Okay. All right. And so this frees up. Sorry, I don't know where to stand so you can see everything. All right. So this frees up the stack pointer. So now I can push and pop things on the stack all I want within the procedure, but the offsets of the variables will always stay constant from the frame pointer. All right. So I would recommend that you use a frame pointer because it makes generating code much easier. Without the frame pointer, you always have to worry about, did I use my stack? Did the offsets of the variables change or whatever? It is possible for the compiler to keep track of what's going on the stack and generate different offsets for different areas within the method. It's just a bunch of extra bookkeeping and extra work that, especially for the compiler for the course project, you don't want that extra complexity. Okay, so are there questions there about the frame pointer? Okay, so now, all right, so we've got setting up the frame pointer. Then the variables are at constant offsets from the frame pointer. So, what else do I have to do in my procedure, right? So to set things up for a procedure call and then to clean things up at the end. So let me see. What should I erase here? I'll just. I'm going to do a different example afterwards, so I can erase this example. All right. Okay, so if I'm implementing function calls, sort of again, I want to think about the high-level issues of, that I need to implement when I need to call a function. And, so one thing that you need to do is to save and restore the values of registers. Right, so I'm in one function and I call a different function, and maybe I don't want all of my registers to lose their values, right? Maybe some of them have important values in them. The other sort of issue with function calls are to pass parameters to the function. Parameters. And pass back a return value, right? So the function can return something. And so we need to implement all of this in assembly language, right? We need to put the parameters somewhere in memory where the function can find them, and then put the return value somewhere where the caller can find it. Okay, and in when we're in JUICE or Java or other object-oriented languages, we also have to worry about dynamic dispatch. And so, this is looking at the type of an object and figuring out, which overridden implementation of a particular method we're supposed to call. Okay, so dynamic dispatch only comes into play for instance methods, so non-static methods in Java. And so I'm going to leave dynamic dispatch until later, after we talk about objects and methods inside objects. Okay, so for now, let's talk about these first two issues, saving and restoring registers. And so typically a language implementation will specify a decision of which registers should be preserved by a function call and which registers the function call can change, right? Often you take about half of your registers and you say, well, these ones I want to keep. I'm going to put important long-lived values in those. And the other half of the registers you use for really short-term values, and it's okay if a function call overwrites them. Right. So for saving and restoring registers, we divide the registers into two classes, and we'll call them caller save registers. Okay, and so these are ones where, so the caller is the function that is doing the call. So these are registers where the callee may modify their values. Okay, and so if the caller, depends on the current values of those registers, it had better save those values somewhere, right? It can save them on the stack, for example. But typically what we would do is for these registers, we wouldn't put any information in them that the caller even needs to preserve, and then you don't need to save them, right? If you just use them for very short-term information. Okay, so these are, whenever I do a function call, these registers may change their value. And sort of traditionally in x86, it's sort of tradition to use EAX, ECX, and EDX. Okay, so sort of the tradition is to use these three registers for short-term values that, if I ever call another procedure, that procedure is free to use them for short-term things and overwrite them with whatever it wants. Okay, and then sort of the opposite of caller save are callee save registers. And so these are registers where if the callee, so the procedure that we're calling, modifies these registers, it must restore them. Restore original values. Okay. All right. So, I mean, the callee has two options. It can either not use these registers and not modify them. And in that case, it doesn't have to do anything. But if it ever writes to one of these registers, these callee save registers, it needs to save its value, or original value first, and then restore the register back to the original value, because the caller of the procedure is depending on the original value being preserved. Okay, and so once again, it's sort of up to your group, and it's your choice to decide which registers you want to make caller save versus callee save, right? I mean, one popular choice is to make every register callee save, and that way, your code can always depend on registers keeping their values. So that's one possible choice. But sort of the x86 tradition, tradition is, well, all the others. So EAX, ECX, EDX are short-term caller save, and the rest, so what do we have? EBX, ESI, EDI, and of course the frame pointer and the stack pointer. Okay, so out of these, really, it's the frame pointer and the stack pointer that are sort of really important to have as callee save registers, right? Because you use these two registers to manage the stack and the current frame on the stack. And you'd probably use the stack to save any caller save registers that you wanted to save. But if you were to lose the stack pointer and the frame pointer, then you wouldn't be able to access any of the data that you've saved on the stack. So, these sort of have to be callee save. I mean, you can probably come up with some tricks where, in some special cases they wouldn't be, but they're, almost always would be callee save. For the other registers, it's sort of up to you to decide which ones to make caller or callee save. Right? And so then the tradition sort of makes 3 of the remaining registers callee save, and 3 of the 3 of the 6 one way and 3 of the 6 the other way. Okay, so then if I if I decide on registers, what about passing parameters and the return value? Okay, so for passing parameters, so this is another design decision where your group can make a decision, right? You can decide, okay, where am I going to put my parameters in memory so that the procedure can find it. But it's one of those decisions that you should make explicitly and write down. So you can put it in your assignment 5 document, but you can start writing that document before you're even close to being done assignment 5. You can make a document for just communicating within the members of your group, right? Because every procedure needs to follow the same convention that the callers of that procedure follow, right? So you need to have a precisely defined convention. So here I'm going to have an example or a sort of a suggested parameter passing convention. And again, feel free to modify it. Feel free to have a different convention. So I'm going to say I'm going to push parameters on the stack Okay, sure. So I'm going to put, so the caller is going to push the parameters onto the stack before it calls the callee. So, I mean, that's a nice convention because then the callee can just look at the top of the stack and find the parameters there, right? So we've agreed on a place in memory where the parameters are going to be. One thing that I need to specify here is the order in which I push the parameters on the stack, right? So, you can push them left to right, or you can push them right to left, or I suppose you could, mix them up, but then you'd better specify exactly how you've rearranged them. In this case, I'm going to say left to right. Okay, and why am I going to say that? Well, I mean, maybe just because that's the order in which they come in the source code. But in Juice and in Java, there's actually another reason for left to right. So the Java language requires the parameters to be evaluated from left to right. Okay, and in general, any expression requires its sub-expressions to be evaluated from left to right. And that's important because the any expression in Java can have side effects. So, evaluating an expression could itself be another method call, and that method could say, print something to the standard output, or change the values of some variables. So the order in which expressions are evaluated matters. It's observable in the behavior of the program. And Java says that you need to evaluate expressions from left to right. So that means the arguments to my method call, I'm going to evaluate from left to right. And so it's convenient to push them onto the stack from left to right, because that way, as soon as I evaluate an expression, I can just push it on the stack and start evaluating the next one. Whereas if they were supposed to be on the stack in the opposite order, I would have to first evaluate them left to right and then kind of reverse them to push them onto the stack. Okay, so but you can pick whatever convention you want. I'm picking left to right because it's convenient. For the return value, well, because it's Java and every value that I could possibly return fits into 32 bits, I'm going to just pick a register, say EAX, and I'm going to say my convention is that when a procedure returns, its return value is always in register EAX. Okay, you could pick a different convention, pick a different register, or leave that return value on the stack, or whatever convention you want. One place where you would need a more complicated convention is in any language other than Java, pretty much. So any language where values can be of varying sizes. So, for example, in C, you could have functions that return a struct, and so that struct could be bigger than anything that would fit in any register. So then you would need a convention that says that the return value is somewhere on the stack, or perhaps on the heap, right? If you had a language where you needed to do that. For Java, every return value is going to fit in register EAX. So I can just keep it simple and make that my convention. All right. Okay, so there's my convention, and now I wanted to do an example. All right, I want to do an example, and I want everything to fit on the board. All right. So, okay, how about I erase this one and get everything to fit. All right. So, okay. So let's say I have a call to a method f, and I'm going to pass x, y, and z, and then the body of f, or the implementation of f, you have way over here, and so f. So f is a function that has three parameters, a, b, and c. Okay, and inside f, I'm going to have a variable I, and I'm going to assign a to it. No, I'm going to just assign 0 to it. Okay, and I'm going to return a. Okay. All right, and so now, maybe I can take a different color and look at how do I generate code for this. Well, okay, so I said I'm going to push, my convention is to push the parameters on the stack before the call from left to right. All right, so to implement the call to that method, I am going to push whatever the value of x is, and y, and z, and I'm going to push these values from left to right. Now, in general, if these were more complicated sub-expressions, I would need to have code here that evaluates the sub-expression for x first before the push. But I'm going to worry about expressions later on. Okay, I wanted a different color. I wanted it to be green. Maybe I'll just stick with blue because it seems to be easier to see in the video. Okay, so I'm going to push these things onto the stack. So I find it really helpful to have a drawing of the stack. For your sort of your discussions within your group, for your internal documents, for your final assignment 5 document, just even just for yourselves, like just visually, get yourself a whiteboard or a scrap piece of paper and have a picture of the stack so you can figure out what code to generate. Okay, so I push x, push y, push z. So, I'm going to have x on the stack, then I'm going to have y on the stack, and then I'm going to have z on the stack. And, after those pushes, the stack pointer now points here, right? That points to z. So, if I asked you, okay, how do I read z? Well, it's at address, ESP plus 0, right? Sorry, ask questions or stop me if there's comments or questions or whatever. Okay, and one thing that becomes obvious when I've drawn a picture is that I push the parameters on left to right, but they actually they actually appear on the stack. If I'm looking from the top down, they appear in reverse order, right? Z first, then Y, then X, because I pushed X and pushed Y on top of it and pushed Z on top of it. So that's something that you might not have noticed if you didn't draw yourself a little diagram. Okay, so I push these parameters on the stack, and then I'm going to have a call instruction, right? So if you remember my x86 instructions, so there's a call instruction, and it takes a constant address. In this case, I'm using f as a label, as the address of this procedure f. or this method f. So I'm going to call f, and then I'm going to be in the code of f. Right? But thinking back, okay, what does call do? So call, well, it's like a jump, so it transfers control to the procedure. But before it does that, it saves the old instruction pointer, the old program counter. It pushes it onto the stack. So the call instruction pushes the program counter, the address that I'm supposed to return to onto the stack. So I'm going to call it EIP here because that's that's the name of the register, but this is the old value of my program counter, and it's now going to be on top of the stack. Okay, and once again, I'll sort of highlight why it's nice to have this picture of the stack, because if you forget about the EIP and I ask you, okay, at what offset from the stack pointer do I find Y? Well, from the picture, you can figure it out from the diagram. But if you didn't have the diagram and you didn't think about the program counter, you might get the wrong offset for Y. Okay, so again, stop me with questions. So we're going to call F, and so we're going to be in the body of procedure F. So, so what am I going to do in F? I had stuff here about saving and restoring registers. Okay, and I'm going to want to save and restore registers, I guess in the current stack frame, but I don't have a stack frame yet. My stack pointer still points to this saved value of the program counter. So probably the first thing I want to do is set up a stack frame, right? So I want to do this this subtraction thing. Or rather, okay. So I can do a subtraction, or I have one variable I in my procedure, so I can use a push 0 instruction to allocate space on the stack for that variable I and put the value 0 in that space, right? Or I could use a sub instruction to subtract 4 from the stack pointer, right? That would achieve almost the same thing. The push 0 overwrites that variable location with the constant 0. Subtracting from the stack pointer would leave that value with whatever happened to be in memory before that. Okay. Okay. And I've got a question and a good question here from Felix. So the question is, before I push X, Y, and Z, I want to save EAX, ECX, and EDX here. Maybe. I want to say probably not, but if those 3 registers have anything important in them, then before you do any of this stuff, then yes, you would want to save those values of those registers on the stack or in some local variables or somewhere. Okay, if those variables have anything important in them. Typically, the generated code has some values that are very short-lived, like you're evaluating some expression and you have a sub-expression that is evaluated and right away you stop needing it. And then they have other values that you need for a really long time. And that's sort of the reason why we have some registers as caller save and some registers as callee save, so that the really short-lived values you would typically put in the caller saved registers. So you would hope that there are no values in those registers that you need for the duration of the call, and then you don't need to save any values. But if you do have a long-lived value in one of those registers, then yes, you would save those registers. So let me write that down. So I'm gonna say optionally save caller save registers. Right. So if they happen to have values in them that you actually need to preserve. Right. And and then I'll repeat again that the set of registers that are caller save, it's your decision. So you could make a decision that none of your registers are caller save. So even those need to be preserved. Although that's going to probably make it hard to implement some of this code, like some of these sub-expressions, like evaluating X, Y, and Z. You might end up needing a register for that. Okay, so in a binary expression, after the left-hand side call, you would move the result into a callee saved one before evaluating the right-hand side so that nothing gets overridden. Yeah, so sort of one way to, let me think about that. So one way to sort of be careful about, not accidentally overriding values in registers is to try to keep things in variables as much as possible, or pushing and popping things onto the stack. So keep things in memory a lot, and only use registers for very short-term things. So if there's anything that's going to survive, say, over evaluating a sub-expression, put it in a variable or put it on the stack. Don't leave it in a register, because you kind of never know when somebody might overwrite a register. And that's on the flip side, using memory a lot tends to be less efficient than registers. So a heavily optimizing compiler will kind of try to do the opposite. It will try to avoid using memory and try to put as much as possible into registers, which is sort of dangerous but more efficient, right? So you live dangerously, you can be more efficient, but you might get hurt if you accidentally overwrite a register that you didn't expect to be overwritten. So there's kind of a trade-off between efficiency of the generated code versus safety or correctness. And for the purposes of the course, I would lean sort of more towards correctness, right? To pass all the marmoset tests, but feel free to depending on your confidence as a group and your sort of sense for adventure, right? To try to possibly generate better code that keeps things in registers more. But keeping in mind that it's going to make it harder to get things correct. Right? You might even have different versions of your compiler, right? There's the safe one that you give to Marmoset, and then there's the fast one. Right? But of course, there's only 3.5 weeks left in the course, so yeah. Anyway, all of that is sort of decisions for your group. Like, how much work do you want to do? How optimized do you want your generated code to be? And how likely do you want it to be that that code is actually correct? Okay, I think that that was a very long answer to a simple question. All right, sorry about that. Got a bit off topic there. Okay, but do ask questions if there's more questions. So here though, so I'm going to push 0 onto the stack to have space on the stack for my variable I, right? I don't need space for the parameters A, B, and C, because those are on the stack. Those were put there by the caller, but I do need space on the stack for variable I. I'll put a comment here to say it's for variable I. Now if I push something onto the stack, that's going to change the stack pointer. Okay, and remember before I erased everything off my board, I said, oh, I want to save the old value of the stack pointer to the frame pointer so that I can keep using my stack pointer and I'll have some sort of fixed address of the current frame. So before I push space for I would like to copy the stack pointer to the frame pointer. Okay. All right, so before I push space for I'm going to copy the stack pointer to the frame pointer. But if I do that, then I've overwritten the frame pointer. And later on, when I return to the caller is going to get mad at me. In fact, well, the caller is going to crash and burn because I've messed up the caller's frame pointer. Right? If the caller over here tries to access one of its variables, well, they're going to be offsets from the frame pointer, but I've just set the frame pointer to point here when before it used to point down here. Okay, so before I mess up the frame pointer, I better save it, and I'm going to save it onto the stack. So I'm going to push the frame pointer onto the stack. So the frame pointer, EBP, all right, is going to be on the stack here. That's going to update the stack pointer to point to it. And that way, before I return to the caller, I can pop the frame pointer. Maybe I'll, start doing that so that my pushes and pops are balanced. Right? So I'm going to push the frame pointer here, pop it back off right before I return. So, at the end, I'm going to pop the frame pointer, and the return instruction, remember, it pops the program counter from the stack and puts that value from the stack into the program counter, and that has the effect of transferring control sort of back to here, back to after the call instruction. Okay, so at the end of my procedure, I'm going to be doing that to restore the frame pointer back to its original value. Okay, so I've pushed the frame pointer. I've made the frame pointer, also point here. So frame pointer now points to its old value. And sort of a rule of thumb, if you're following this convention, is that the frame pointer always points to the value of the previous frame pointer. So that's actually kind of nice, because then the frame pointers kind of form a linked list of frames. Like if you want to, do a stack trace, look at what other frames are on the stack, you can just follow, this frame pointer has the address of the save frame pointer of whoever called the caller of F. Okay, so now that I've pushed the frame pointer, then I push a 0 for I. So then I is going to be here, and the stack pointer is going to point to I. And the frame pointer is down here. After I've done that, now I can push any other callee saved registers. Right? So I'm going to put this as a comment. So I'm going to say push callee saved registers. Okay. So, again, it's up to your group to decide which registers are callee saved. And it's also optional. If the procedure doesn't use a particular register, then you don't need to save it and restore it. I guess to be safe, you could save and restore all the callee saved registers. But if you're trying to optimize things, if there's registers that you don't use, you don't need to save and restore them. Okay, and since I pushed, I should pop them off again. Oops. Sorry, so at the end, I should pop callee saved registers. Okay, but like, what did I forget? So I have push, 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 and here I have 2 pops to balance it out. So that's bad, right? So sort of the one of the key things of generating code or even writing assembly language code by hand, always make sure that your pushes and your pops match up, right? Because, as soon as they don't, your stack is going to get totally messed up, and, things are just going to go crazy, and those are really hard to debug. So always keep in mind, whenever I write a push, put a pop to replace it. And in this case, I'm actually going to do something a little bit different than a pop. And I'm going to move the frame pointer into the stack pointer. Okay, I mean, this is an option. I could say, okay, well, here I pushed 1 word, so here I need to pop 1 word. But kind of a quick way to pop the entire frame is to take the frame pointer, and remember the frame pointer always points to the bottom of the frame. It was the thing that I set before I started pushing things onto the stack as part of the current frame. So here, if I copy the frame pointer into the stack pointer, then that puts the stack pointer to where it was here at the very beginning. Okay, and so one nice thing about this is, if I was in a language like C, where I might push extra things onto the stack, I might not even know how many things I pushed onto the stack, then this kind of an instruction would pop off as many things as I happen to have pushed since the time that I set the frame pointer. So the instructions that I have here, kind of especially these and these are kind of an idiom. If you look at random x86 code generated by whatever compiler, you will often see this pair of instructions or this sequence of instructions or idioms like this that indicate, okay, I'm at the beginning of a procedure or I'm at the end of a procedure, right? So if you're reverse engineering x86 code, you'll frequently see these patterns. Okay, so I have my prologue. So this part of this code that sets things up at the beginning of a procedure is called the prologue. My epilogue, the code at the end that cleans things up and returns back. I guess, I should generate code for the body of the procedure. In general, there's going to be a lot of juice code, so I'll need to generate a lot of code for it. But in this case, the only real code to generate is return A. So I need to figure out where A is and where all my variables are. So, let's see. So and I'm going to be doing offsets from the frame pointer. So my variable I is at the frame pointer -4. right? It's right before the frame pointer. And yeah, all right. And what about my parameters? Well, I have z, y, and x, but really they're the parameters c, b, and a, right? So this is frame pointer plus 0. Frame pointer plus 4 is the instruction pointer. So frame pointer plus 8. So EBP plus 8. Okay, and if I draw myself this little diagram, I've got EBP plus 12 and EBP plus 16. All right, so to access parameter A, I just use EBP plus 16. So here I want to read A. And then I'm returning A, and my convention for the return value is put it in register EAX. So I'm going to do a move EAX, move the value of A into register EAX. Okay, and that's how I'm going to set the return value. Okay, so does that make sense? Sort of generally how this whole layout works. Once again, drawing diagrams is helpful, and sort of comparing the code that you want to generate to your diagrams. Now, there's one more thing I forgot here. Can anybody remind me of the one thing I forgot in terms of the code that I need to generate for this example? Okay. So, if I run all this code here, so it's going to put the value of A in EAX, then it's going to pop any registers, then it's going to set the stack pointer back to here. So, okay, stack pointer's here. Then it's going to do the return, which is going to pop again. So now I'm going to be back at the call site, and my stack pointer is going to be here. Oh, but I popped the frame pointer. So the frame pointer I will have fixed. So the frame pointer, points to wherever the frame of the caller is. So the frame pointer is all fixed up, but the stack pointer points here. And is that where the stack pointer is supposed to point? Well, I mean, before the call, the stack pointer pointed here, and I pushed these 3 values here. And remember, if you push something on the stack, you better pop it off again. So, over here, I want to pop 3 times. So, or add 12 to the stack pointer, and that would pop off the values of A, B, and C. Whoops. So that would take my stack pointer back to here. Okay, so I need to, whoops. Sorry, I want to add 12 to the stack pointer, right? To pop 3 times 4 bytes off the stack. Okay, so, or I could write, 3 pop instructions to get the stack pointer back. So that's another part of the convention, and maybe another thing to write down is sort of whose responsibility is it to pop the stack, right? Should the caller pop the parameter values off the stack, or should the caller, should the callee pop them off before it returns? It's again, it's your decision. So you decide amongst your group and write it down so that everybody knows what the convention is. One reason why it's kind of convenient to do it this way is that above the parameters is the program counter, and for the return instruction, you need that value of the program counter at the top of the stack. So if you start popping before the return, you're going to mess up the stack for the return instruction. Having said that, the x86 return instruction actually has an extra argument. So you could tell it return and pop some number of bytes off the stack. So it has a way to do that. So you can say like return 12, which would pop EIP off the stack and then pop another 12 bytes. So you could pop the arguments in the caller instead of the callee, but doing it this way works as well. So just as long as you're consistent, right? Either the callee, either the caller has to do it or the callee has to do it. Okay, so I'll stand to the side. Are there any other questions about this sort of general call and return mechanism, right? Because having this layout worked out and sort of knowing where variables are and being able to access variables is sort of the key. Also you need to go and figure out what code to generate for each expression, and I'll talk about that as well in future lectures. But a lot of that, right? Figuring out what code to generate for an expression, a lot of that you can at least partly figure out as long as you know where all your variables are, right? So like knowing that the parameter A is at offset 16 from the stack, from the frame pointer. Okay, so any questions about the layout here? Right, okay. I have one more comment here. So for Juice, I decided to use a left to right ordering of the parameters, and I talked about why that's convenient, because that's the order in which you have to evaluate them. Many languages put the parameters in the opposite order, and one sort of prominent language is C. So for C, the convention is almost always backwards, so right to left. And the reason that C uses that convention is to accommodate functions with variable length argument lists. So functions like printf in C, where a printf can have any number of arguments. And so then the idea is that you put the first argument at the top of the stack, and the second argument just below it, and the third argument just below that, and the nth argument for some unknown value of n, n words down. And so by pushing the arguments right to left, you can have any number of arguments, and yet the nth argument or the ith argument is at offset I, or I guess I times 4, but at some offset from the top of the stack that you can determine based on I. Okay, so it is very common to have the opposite convention, right to left, but for Java and Juice, it's convenient to go left to right. And if you don't have to support variable length argument lists, then either direction will work just fine. So I guess we've got the layout of a stack frame, and I don't know, I've got a few minutes, I've got 10 minutes left, and so I also want to talk about laying out objects. But I have a question. So the question is, doesn't Java also have the variadic arguments feature? So yes, so Java also has this ability to pass, to have functions with unknown numbers of arguments. I'm pretty sure Java 1.3 didn't have that, or did it? Did you see it somewhere in the Java language spec? I'm pretty sure it was added later, but even later, the way that Java deals with it is that if you have a function that has a variable number of arguments, it actually creates an array to hold all of the extra arguments, and it puts that array on the heap. And then there's just one argument to pass, right? Just the address of the array, but the array can be of any length. So Java sort of goes around it by allocating an array object, right? Whereas C, tries to not use the heap too much and tries to keep things on the stack. So it's kind of a different implementation. But yeah, I think it's only later versions of Java, and definitely Juice does not have this feature. So we don't have to worry about it in the Juice compiler, and yeah, I can't remember which version of Java added it, but yeah, so even the later versions of Java don't have to implement things like C, because they can create an array and put the arguments in the array. Okay, I do want to at least start talking about objects, and we'll have time to finish objects on Wednesday. So what do I write? Okay. So laying out objects. Okay, so last week we talked about why you would put objects on the heap. So local variables and stack frames we're putting on the stack, but objects we're putting on the heap because they can be allocated at any time during the execution of our program. And we don't know how many objects a given piece of code is going to allocate. Okay, but when I'm deciding how to lay objects out in the heap, there's a key consideration, and that's subtyping. Okay, and this notion of subtyping is going to drive my whole design process of how do I design the layout of objects. So that's why I'm starting with that. And so the idea is if S is assignable to T, so if I have two types, S and T, right, and this is the assignability relation from our type system. So if I have any two types where S is assignable to T, then if I have a variable of static type T, can hold a variable, can hold an object of dynamic type S at runtime. So can hold object of dynamic type S at runtime. Okay, so I mean, why is this important? And why does this matter? Well, so the compiler is generating code to do things with variables, right? To evaluate expressions, and those expressions refer to variables. And the compiler only knows the static type of a variable, and more generally, the static type of any expression. But if the static type of a variable is T, the actual dynamic type, right, the actual object that is in that variable could be, any type S that's assignable to T, right? So if I have a variable of type fruit, right, I might store an apple object or an orange object in that variable. Okay, So, so what does this mean? So, well, that means that all the objects of all the various types S that are assignable to T have to have a compatible memory layout. Okay, because the compiler is going to generate code that for all objects that could be stored in that variable, and it's going to look in specific places of memory for, say, the fields or the methods of that object. And no matter whether the object is an apple or an orange, it needs to have those fields and those methods in the same places at the same offsets. Okay, so the key idea to achieve that, well, okay, so layout of S must be compatible with T. Okay, and so the way that we're going to achieve that, or at least we're going to try, this won't always be possible, but whenever it's possible, we'll try to do this. We're going to make the layout of T a prefix of the layout of S, right? For every pair of S and T where S is assignable to T. All right, so, to put it another way, again, if I go back to my fruit analogy, if I have apples and oranges, well, for an apple, I'm going to first store in memory all the fruity aspects of my apple. And after all the fruity stuff, I'm going to put the apple-specific stuff. And same thing for an orange. I'm going to put all the fruity stuff first, and then all the orange-specific stuff afterwards. And then, that way, if I don't know whether I have an apple or an orange, if I only know that I have a fruit, well, that's fine. I can still access all the fruity stuff of a fruit, because it's going to be at the beginning in a consistent order, in the sort of the order determined by the fruit type. And whatever comes after it, I can ignore if I'm only concerned about the fruity aspect of the apple or the orange that I happen to have. Okay, so that's a sort of high-level description of why I want the layout of T to be a prefix of the layout of S, or to flip it around, right? If T is the fruit and S is apples and orange. So when I'm designing the layout of an apple, I'm going to take its supertype fruit and, use fruit's layout first, and then add more things after it, right? After that prefix. And so now I have to think about what are all the things that I want to organize this way. And so where am I going to put it here? So what is all the data that I need to lay out in this way? And we already talked about this last week, but we're going to have the per object data, right, and the per class data. So some data is specific to each individual apple that I have. So these are going to be the values of the fields, right? So let's say instance fields. Okay, but you also have the class tag, which is a address of the per class data. And the one important thing that you have in the per class data is the method implementations, right? So all apples have the same, body of a particular method, right? Like an eat method. And, there's a few more things that we had in the per class data. So the point is, both the per object data and the per class data is going to have to follow this principle, that the layout of T is a prefix of the layout of S. So for an object, for each apple object, if apple is a subclass of fruit, each apple object is going to have to be a fruit object plus additional stuff after it. But then from an apple object, I might follow the class tag pointer. And at this point, I still don't know that it's an apple or whether it's an orange or whatever. So this per class data, so the per class data for an apple has to be, again, an extension of the per class data for an orange. Because if I want to call a method on an apple, I'm going to look in the per class data for the apple. And but if it's a fruit method and I only know at compile time that I have a fruit, then I'm going to look in the offset in the per class data for a particular fruit method. So that the apple per class data needs to follow that. Okay, so both the per object and the per class data needs to follow this prefix rule. And I know this is abstract and maybe hard to see, so I have a specific example, and I want to show it to you, but I'm out of time for today, so I'm going to leave this on the board, and in Wednesday's lecture, I'm going to talk about, I'm going to show you a specific example, right, of how we can actually lay out the heap space of some specific objects and some specific classes. So the examples coming, are there any questions about any of this before we finish for today, and then I'll continue this on Wednesday. So any questions? Last call. Okay, so remember assignment 4 today, and especially the document for assignment 4. If you don't get assignment 4 done, do at least write a document to tell me about how you did on assignments 2 and 3, what you did, what your design was. So I really want that assignment 4 document today. If you don't get the code done, start working on code generation assignment 5, and you can come back to assignment 4 later and finish it for the late deadline. So questions, last call? Okay, well, we'll be back on Wednesday, so have a good couple of days, and have fun implementing the code generation, and I'll see you again on Wednesday. Okay, bye.